Hi. So we're towards the end of the chapter, and 5.7 is yet another way to calculate delta H. This is calculating delta H from something called the enthalpies of formation. So these are, or how an enthalpy of formation is defined is literally the formation of that compound, the formation of the compound from its component elements. The standard enthalpy of formation is always, it makes 1 mole of that compound at its standard state. So that is the state that it's found in nature, and 298 Kelvin. And the delta H of formation of most stable forms of an element is 0. These numbers, the delta HFs, this is in the appendix in the back of your book. There's a big table of them. And you're going to want to refer to that table. The table of delta H of formations is Appendix C in your textbook. It's page 1100, and you're going to need to have that handy for the homework. So if you're doing this before we've had class, I will pass out Appendix C, a photocopy of Appendix C, so that you can always have that handy. And all these numbers would then be given to you for on like an AP test or something. So the first question is just which of these are standard enthalpies of formation. So remember that it needs to be for 1 mole at standard state. So if I look at A, it's talking about making sodium oxide. It's making 1 mole of sodium oxide, and everything is in the state of matter that it's found in nature. So this looks good. In B, you can see that it's making 2 moles of the compound. So this is not a reaction that would be the standard enthalpy of formation. You would need to divide everything by 2. And in C, the standard enthalpy of formation would be this guy, but we would need to switch it around, right? So that it was the formation of C6H12O6. And also, the standard state of carbon is not carbon in the form of a diamond. It'd be carbon in the form of a graphite. So that's how those three are not, the first one is, but the second two are not standard equations that symbolize the standard enthalpy of formation. So let's, how are we going to do this? Well, this is the formula that we are going to use. This is on your equation sheet. But it's pretty important that you actually have it in your head, because you're going to need to use it a lot. And we're going to use similar equations to this for the unit that comes back around to thermodynamics at the very end of the course. And we will be looking at changes in enthalpy and Gibbs free energy. And we'll do the same thing where we do products minus reactants. And so how we figure out the standard enthalpy of formation is we look them up in the table, and then we do products minus reactants in order to find the delta H of the reaction. So here's a small subset of Appendix C. So these are the ones that you need in order to do the practice problems, but the homework problems, you need to use the full appendix here. Sometimes they're positive, sometimes they're negative, and they are always in kilojoules per mole. So if this reaction, or if we're thinking about this reaction here, right, of C3H6, so this is the combustion of propane. If we're to think about this reaction, think about what we would be starting with. So here are the reactants, right? And the first thing that would happen is we would decompose those into its elements. So this is like, think of this as almost Hess's law. So we would need to add 10(3O5) to make them into their elements. And then we would, the second step would be the formation of 3 carbon dioxide molecules and 4 moles or molecules of water. If I add up 1, 2, and 3, think of what these are. It's the opposite of the formation of the reactant. So that's why it's the second half of our equation is minus the delta H of formation of the reactants. And then the first part is adding up the formation of all the different products there. So that's why it's products minus reactants. And if I were to add up those two, we would get the delta H of the full reaction. Okay. So this says calculate the standard enthalpy change for the combustion of 1 mole of benzene to carbon dioxide and water. So the first thing I should do is I should write a balanced chemical equation. C6H6 plus O2 yields CO2 plus H2O. And the states of matter do make a difference here. So I need to balance this. So I'm going to put a 6 in front of the carbon dioxide, and I'm going to put a 3 in front of the water. And that balances out my carbon and my hydrogen, but my oxygen are not quite balanced yet. This tells me that it would be 12 plus 3, or 15 oxygen that I need to have on both sides. I'm going to put this as 15 over 2. And last year, and even this year, we had this trick where then we multiplied the equation by 2 so that they were all whole number coefficients. We really don't want this in this case because it says calculate the standard enthalpy change for the combustion of 1 mole of benzene. So I want to actually leave these coefficients the way they are. And then that will tell me the delta H for the reaction, and the reaction is reacting 1 mole of benzene. So now I apply that formula, right? Delta H for the reaction is equal to the delta H of formation of the products minus the delta H of formation of the reactants. So now I just am going and I'm looking in Appendix C or on the table before for the numbers. And I'm starting with the products, so 6 times, and I find the number for carbon dioxide, it's negative 393.5 kilojoules. In the table, it's listed as kilojoules per mole, and then when I multiply it by 6 moles, those moles will cancel out. So generally, I just don't write the moles in because they're going to cancel out for every single one. And then the other product is 3, and liquid water is negative 285.8 kilojoules. So those are the products minus the reactants. And the reactant is going to be 1 times benzene is 49 kilojoules. And then plus, and if you look at that table, you'll notice that oxygen isn't listed, but that's okay because remember the standard enthalpy of formation for elements is 0. So they will often just not, I mean, they don't put it on the table, and students who forget that don't know what to do. They're like, I don't have enough information to answer this question. Sometimes they'll put a multiple choice down, and one of the answer choices will be there's not enough information to answer this question, but there is, because you don't need to know the standard enthalpy of formation of oxygen because it's an element. So now it's just arithmetic, and although it's just arithmetic and you will be able to use a calculator, often students get these problems wrong because it's just computing, but you have to just really be super careful with signs and making sure that you plug the numbers in your calculator correctly. So when I multiply this out, I get negative 2361 kilojoules plus negative 853.5 kilojoules, and then minus 49 kilojoules. When I add these up, I get negative 3,266.5 kilojoules. B says compare the quantity of heat produced for the combustion of 1 gram of propane with that produced by 1 gram of benzene. So this is a little different. So we are going to have to take some data that we have and convert it, because this number, negative 3267 kilojoules, negative 3267 kilojoules is for every 1 mole of that benzene. So if I need to convert that to grams, right, kilojoules for gram or for 1 gram, I would need to do 1 mole of benzene, and the molar mass for benzene is 78.108. Right? So just treating this like dimensional analysis, these units cancel out, and so my answer is negative 41.8 kilojoules per gram of benzene. And the question says compare the quantity of heat produced by the combustion of 1 gram of propane. So we actually know the delta H of combustion of 1 gram of propane from this. So because, you know, these are the reactants, this is propane, this is reacting 1 mole. So negative 220 kilojoules per mole. So 2,200 kilojoules per mole of propane, C3H8, and I convert that into kilojoules per gram, and the molar mass for propane is 44.094 grams. When I do this, I get negative 50.3 kilojoules per gram of propane. So I get more energy per gram of propane than I do per gram of benzene. Okay, practice, another practice problem here. And this is a multiple choice. Calculate the enthalpy change for the reaction of hydrogen peroxide decomposing using these enthalpies of formation. So, you have to think delta H is going to be, products minus reactants. So 2 times water, which is negative 285.8. That's the product, right? Another product would be oxygen, but that's going to be 0. So minus the reactant, and that's 2 times negative 187.8 kilojoules, right? And then if you think about, putting these together, it's going to be, this is going to be minus and negative. So it's going to be negative, 500 and something minus, a little less than 400. So, or a little less than, 400. So you can sort of estimate, or you can have a calculator and figure out that it's going to be certainly negative and negative 196. Okay. And this is another one for you to try. It's very similar. Use table 5.3 in order to calculate the energy of combustion of ethanol. So I'm going to leave this blank because I don't want this to be too long. Do this problem out. I'm going to tell you right now. The answer is negative 1367 kilojoules per mole. So see if you can do that. Pause the recording. See if you can do that and get that answer there. Because the next problem is a little different. It gives you the standard enthalpy change. So I'm giving you delta H of reaction, but I'm asking for a delta H of formation. Again, this is no different. This is just formula, plug in, and solve. But this time I have I have the delta H of reaction. So this is 178.1 kilojoules. The delta H of the products, the question's asking me to solve for the delta H of formation of this. So the products are 1 times, and I look on the formula, I look on the table, and I get negative 285.8 kilojoules. Crap. So I look at the products because it's products minus reactants. So the products is 1 mole times the delta H of formation of calcium oxide. I look on the table, that's negative 635.5 kilojoules. And then the other product is carbon dioxide. So 1 times negative 393.5 kilojoules, right? And it'll be products minus reactants. And this is what I want to find. The delta H of formation of CaCO3. So I add those two numbers together there. I do, and that comes out to be negative 1029 kilojoules minus the delta H of formation of CaCO3. I would add that number to both sides. So negative 1207.1 kilojoules equals the negative delta HF of CaCO3. So that means positive 1207.1 kilojoules is equal to the delta H of formation of CaCO3. So you can also solve for a one of those delta H's of formation. And that's actually what practice exercise 2 is. It's asking you to do the same thing, calculate the standard enthalpy of formation of copper oxide. And this is one I will tell you the answer again of this problem is negative 156.1 kilojoules. So try this problem out on your own, see if you get that answer.